Okay, well, this better work. Okay, so yeah. Number one, we're given this situation. We've got a function for revenue, a function for cost, and first it wants us to find R prime and C prime. Okay, so this is just taking the derivative. So there's nothing too bad about that, except for the interpreting of the meaning. That interpreting, well, I'll say what I wrote, but okay, 0, 0, 0, and then you've got a 2x, right? All we're doing is power rule. And as for the meaning, so maybe first I'll put the units down for this. So this is dollars per day toy. And the meaning of this function, I put that this is the rate of change of revenue. If for selling X toys. Right, that's basically what this function R prime represents. I don't know necessarily if this is actually like, there might be other ways of phrasing this answer, but it should roughly be something like this. Okay. And then, well, the function for cost, take its derivative. You see that you just get a constant is equal to 2. And this is also going to be dollars per toy. We can say a little bit more for this one. So the rate of change of cost, since this is a constant, we can just write this as being that constant. So $2 per toy. And another way of phrasing it is if you increase the number of toys by 1, then the cost will increase by $2. Right, just another way of interpreting what this is saying. Okay. Let's see. For the next one, I actually wrote this as being a profit function. Yeah. So hopefully you know that. Maybe I'll put it off to the side. So you should know that revenue minus cost is something that you usually call the profit. So you just define that. Maybe make that look a little bit better. Cost. Okay, and so this is really asking for the derivative of the profit function, since you can take the derivative and split it. So I'll just say p prime of x, which is what that is asking for. That's just going to be r prime minus c prime. So maybe I'll also write that r prime minus c prime, just showing a little bit of extra work. And then you subtract. So then you would get 8 minus 0.0002x. Okay. And yeah, interpreting rate of change of profit. And perhaps also we should put units down. So this should be dollars per toy. Okay. Questions so far? So D, when is the derivative that you found positive and when is it negative? So, okay, I'm writing it like that. Sure, I'll write it like that. So P prime, when is it positive? Well, that's going to happen when, so I would say this is greater than 0, and then you just move it to the other side. So you get 8 is greater than 0.0002x, which well, then you multiply over or divide over. X has to be greater than 40,000. Let me check that makes sense. 1, 2, 3. Add 3 zeros divided by 2. 4 zeros. Add 4 zeros divided by 2. Yeah, okay. And the units for this is toys. And for the other half, when is it less than 0? Right, almost the same thing, just use a different inequality. I can probably put the commas there just to make it more legible. Okay. Right, and so E is pretty much asking us to think about D. How do we maximize the total profit? So this is saying that the profit will be increasing. Wait. Hmm. That's a bit weird, isn't it?
For D, I actually got the other way around.
Yeah, that's what I'm noticing. Something is wrong with my inequalities, right?
That made more sense when I got to E, I guess.
Yeah, but then what did I do wrong algebraically here? Adding to the other side, and then you can divide it by dividing by I see. The x stays on the right hand side, so then I flip the whole thing around. So actually, it should be less than, and this should be greater than. So do you understand that this is true algebraically? Like I'm doing like 2 steps in one. That's why I got confused. Right, so first we would divide this number over, but then the inequality is pointing towards the x, so it should still be pointing towards x when you swap the order of the inequality. I'm like reversing the whole statement around. So this is true. Yeah, and it also makes sense intuitively because we expect that the profit goes up up to a certain point and then it starts decreasing once the quantity goes. So yeah, when we interpret this, then this is saying profit is increasing as long as the amount of toys you're producing is less than 40,000, but then greater than 40,000, you've got the profit is now decreasing. So to maximize the profit, um, how many toys should you produce? That should be 40,000 to maximize profit. And to figure out what is the actual profit that you produce, you plug that into the profit function. And do we have the statement of the profit function? No, we just have to plug that into R minus C. I sort of split that out. So pretending that we actually um, computed these, you would actually get 240,000 for the revenue, I think, and then 130 for the cost. And so then this is going to give you 110,000 total profit. And for explanation, well, for explanation, it's pretty much what I said out loud, but after x is equal to 40,000, you have that the profit, the rate of change of profit is negative, so profit will decrease. Uh, beyond that point, I guess. I can add on. Okay. So does this whole problem make sense? Are there any questions? Okay. If not, then keep going. So number 2, this is a sort of a real world type of thing. So you're given a cup of hot tea, and this is just saying what is the rate of change of the temperature going to be 3 minutes after, right? 3 minutes after you got your cup of tea. So hopefully everyone can just answer this. Right? This is going to be negative, since your tea can only get, can only decrease in temperature. Temperature will decrease because temperature will decrease. Right. Versus if they gave you a glass of, like, I don't know, soda with ice, then you expect that the temperature will increase. It's all because of the ambient temperature versus the temperature of your beverage. Okay. Right. What sections? This is called like applied derivatives or something. So it's just asking you to interpret this statement. Just write it all out in words. So okay. How did I write this? In 2018. So hopefully you like have thought about this. You have to untangle every number here and use pretty much all the words that are in here in the sentence. So in 2018, and that's because this is being plugged 18 years after 2000. The water in, you have to be specific since it tells you where. Little Creek Lake is decreasing at a rate of 0.01 cubic kilometers per year. Right, so decreasing at a rate is because it's W prime and because you've got a negative there. So that is how you would re-express the whole problem in words. Does that make sense? Okay. No questions. All right. Then number 4, equation of a tangent line. So this is something you should remember how to do, the whole process of finding the equation of a tangent line. I guess the only difference here is now we have cosine. Because you learned at this stage, you learn about the derivative of sine and cosine. Maybe I'll say one thing about that. Let me actually scroll over. So you learned that the derivative of sine is cosine. Did you guys go through all of the trig derivatives? I'm trying to remember. Cosine. Derivative of cosine is negative sine. And I think you also learned tangent, right? Is secant squared. Can someone confirm?
Yeah, we learned all of them.
All of them. Okay. So I'll lay out all of them just so that everyone can have this as a reference. So you've also got cotangent's derivative, which is going to be negative cosecant squared. Secant's derivative is going to be secant. Actually, for this one, I really want to put the x, tangent x. So I'll put secant x's derivative. And then cosecant's derivative is negative cosecant cotangent. Okay. And I'm writing it in this way because there's more patterns when you write it in this kind of grid-like fashion. Things split off into families like this. So you can see that structurally sine and cosine kind of behave the same. Tangent and cotangent behave in the same way. Secant and cosecant behave in the same way. And you also see that for the functions that start with so cosine, cotangent, and cosecant, you have a negative showing up when you take its derivative. This is just a way to like remember every single one of them. Although on exams, we only usually make sure that you just know like the first column here, sine, cosine, and tangent. But then eventually you'll probably, if you go high enough in your calculus curriculum, you'll learn that you kind of just need to know the others as well. So I'm just showing you all of them. And when we get to it, there will be inverse trig functions, the arc trig functions, and they also sort of exhibit patterns when you write them out in this way. We'll see that eventually. Yeah, so you learned this. One other thing I can say is, you learned that when you take repeated derivatives of sine and cosine, they'll start to cycle back. But for whatever reason, they don't write it as a circle, which I found really bizarre because you can just write it as a circle and you just see that it'll cycle, right? Negative, and then, so this is me taking a derivative for each of these arrows, right? You can see like it'll cycle. Right? Sine's derivative is cosine, cosine gives you negative sine gives you negative cosine will give you doubly negative sine, so two negatives will cancel. So just as long as you, okay, I'll preempt this. So we're learning derivatives now. Halfway through the course, we will start to learn integrals, where basically you're going to be asked to go the other way around. You want to find the opposite thing. You're given what is the derivative. You want to find what thing will give you that as a derivative. And so you start to need to like be able to run this thing backwards. And a lot of people will get tripped up when you start to try to take the integral rather than the derivative. So one way to keep things straight is you memorize this order for derivative and make sure that you don't forget this order when you start to go in reverse for integrals. But anyway, let's come back to this. Right. So the process for finding the equation of a tangent line. I actually remember my grader saying that a lot of people, they didn't read the problem correctly for like, I guess homework 1 or maybe, I don't know, whichever one you just got back. So equation of a tangent line, it's not just finding the slope. You also need to then write it in the form of an equation, right? Point slope form. You still have to put things into point slope form afterwards. The first step of the whole process is finding the slope. So yeah, first we do the derivative, which in this case, well, derivative of cosine is negative sine. So you're going to have a negative come out. And so you got negative 5 sine of x. This would be the derivative of the whole function. But this problem is asking for the derivative at a specific place, at x is equal to pi over 4. So we want to now plug into this derivative function. Okay, and so now we have to quickly think through unit circle, and hopefully you can remember pi over 4, that's 45 degrees. Sine is just going to be root 2 over 2. Okay, so this is the slope. We can just write this as m, and we have the point. Oh, well, we almost have the point. We still need to calculate something about it. So we need to calculate y of pi over 4. Right. Well, cosine behaves in the same way. So we actually get 5 root 2 over 2. So our point is pi over 4, comma, 5 halves root 2. And now we just plop this into point slope form. Y minus y naught, which is this guy. So 5 halves root 2 is equal to m, negative 5. I guess I can put the root 2 out. Or 5 over 2. Yeah, okay. And then x minus x naught. So then, like so. And this is the answer that the question is asking for. Okay. All right. Any questions? No? Okay. Probably want to go further if you guys want to. Number 5. So we're just going to keep taking derivatives. So hopefully the first thing that you notice about this is that you have to use product rule. right? This is a product of two functions, the x and the sine. So taking the first derivative, we're going to get sine x plus x cosine x. Right. That was just application of the product rule. Maybe I'll say v prime of x just there. Okay, then the second derivative. So I look at the first derivative and I just go ahead and take its derivative. So the first term, its derivative sine will be cosine. That's fine. The second term, we have a product rule. So we're going to have two terms come from this. So the first thing is I would take the derivative of x, which will just leave me with the other guy. And then I don't take the derivative first, instead I take the derivative of the second. That's going to give me a negative sign. So I'll flip the sign here. Okay, so now we have a sine x. And to make things a little bit nicer for the third stage, I would actually rewrite this, clean this up a little bit. So because you've got two cosines in common here. So we have a 2 cosine x minus x sine x. Maybe I'll box this one since it's a little bit unclear, right? And now for three derivatives, actually, you can just write triple prime. You don't need to put that in parentheses. It only gets unwieldy at 4, I think. All right, so then first the derivative of the cosine, that will be negative sine. So we get negative 2 sine. And for this one, we also have a product rule. The negative is going to distribute over both terms. First, we take the derivative of x, that'll give you the other function. And then you leave the x, you take the derivative of sine, which gives you cosine. And you could leave it in this way, but it's not so bad to just simplify it a little bit. It'll make it look a bit nicer. So minus 3 sine x minus x cosine x. And I think if you wanted to, you could actually see if there is a sort of a general pattern of some sort that's going on. Let me box this guy as well. Okay. I think I have a lot more time than I would have expected. Wait, am I sharing the whole screen or am I sharing? Okay, I'm just sharing the one note. Yeah, okay, so we're only halfway through our recitation. Do you want me to just go through everything else?
Yes.
Yeah, okay. So I might only be able to get through half of 6 or maybe all of 6, but I doubt that I can get all the way to the very end. So anything you missed, just watch the second recitations video. Okay. If you want me to step through this carefully so that you can understand everything, it's going to take a bit of time because these are somewhat complicated looking, right? So this is quotient rule. Hopefully you can see that, right? You've got a quotient of two functions, and then it's just putting a sign in there just to make you guys practice, I guess. All right, so do you remember quotient rule? I want to make sure you guys remember, because the sooner that you memorize these things, the better. All right, maybe I'll write it off to the side. I guess you're going to forget. So derivative is in this order over g squared, right? So one way or the other, you have to memorize this order. Yeah, don't switch the subtraction. Okay. So I copy the denominator just as is, sine of w plus 14w to the 9th, and then multiply by the derivative of the numerator, which is pretty bothersome. 45 over 7w to the negative 2 sevenths. Plus 5 minus. So just to make sure, everyone, do you follow how I got these two numbers from taking the derivative here? It's only power rule. Yeah, okay, great. And then the other half of quotient rule, which I'm gonna run out of space for, 9W5/7 plus 5W plus 4. Let's bring that multiplication over. So then now I need to take the derivative of the denominator. That's going to give me a cosine of W. And then I calculated that number before. So plus 126 W to the 8th. And it's both of these things together. Okay. And then this is all divided by the denominator squared. So that's the sine W plus 14 W to the 9th all squared. Okay. So that is A. B should be pretty much the same. Well, okay. They're making it tricky because now you've got a product rule inside of a quotient rule. Right. Well, we can still do that. If I use a different color, maybe it'll be easier to tell them apart though. So copy the denominator, derivative of the numerator. So, right. If I take the derivative of the sine first, we'll get a cosine times cosine. I'll just combine those together, say cosine squared. And then we got a plus, and then it'll be sine times negative sine. So if we were to have thought ahead, this would be actually a minus sine squared theta minus, and then sine theta cosine theta times the derivative of square root theta. And if you're used to the pattern, you will immediately write that as the derivative of the square root of a function or of some variable, right? If you don't immediately know that, then you remember that square root is a 1/2 power. You use power rule, so then you get 1/2 theta to the negative 1/2 power. But then if you rewrite it, you'll end up getting that. And then the last part of quotient rule is you square the denominator. So that's just going to get rid of the square root there. You'll be left with theta. Yeah. Okay. I'm just checking myself because I wrote something slightly different in when I did this on paper, but I think I'm right in this case. Derivative cosine will be negative, so this should be negative. Yeah. All right. Oh, well, so usually when I explain this, what I have to tell people is to really to rewrite this. So you've got this cosine function, and then you're raising the entire function to the 7th. So because this notation makes it easy for you to confuse yourself when you're taking the derivative. I see a lot of the time people take both derivatives at the same time. They take the derivative that raising to the 7th power at the same time as they take the derivative of the cosine. But actually, this is a chain rule, which is one of the later, I think it's like the third topic of this week is the chain rule. So I guess I should talk about chain rule briefly. So if you remember, chain rule is the rule that you use for when you have a function inside of another function, if you're trying to take the derivative. So what you do is you take the derivative of the outermost function and you leave the contents of it inside. Then you have to sort of peel away the outer function, and you now are dealing with the derivative of the inner function. And this extends to if you have more nesting. Right? So if you have a function in a function in a function, then the way this works is you take the derivative of the outermost guy, leave the inner stuff the way it is, but then you have to take the derivative of the inner function, which in this case, so here maybe color is helpful. Then you take the derivative of the inner function. That's the rest of the what I call the chain rule piece times h prime of x. So you see like that we take away the f, and then we're left with the derivative of the g. Then we take away the g, we're left with the derivative of the h. It's kind of unraveling the function as we go. And we just are multiplying all of these pieces together to form the derivative. So this triple nesting is what you get for part f, right? This one over here. But this one is just one function inside of another, the cosine function inside of the raising to the 7th. And I also actually would need to do that for the tangent squared here. So this is actually the tangent function that is then being squared. So once you actually get like comfortable with it, you may not need to rewrite these things, but you still have to pay extra attention because it's very easy to mess up taking this derivative. All right, so first for this, we would do power rule, right? So that's going to give me a 28 cosine to the 6th. So I can use the shorthand cosine to the 6th x. But notice now we have to take that derivative cosine. So that's going to give me a negative sign, which is the thing that you might forget to do. And secant's derivative, well, that's just one of the things you should remember. I wrote that up here. So secant's derivative is secant tangent. Very helpful to just immediately recall that. So we write down secant x, tangent x. And then, well, we have 78 tangent squared. Okay, so first we would have the power. We have that squaring. Take the derivative of raising to the 2nd power. That's going to multiply the thing. So we would have 156 tangent x, and then we have chain rule. Okay, so then chain rule says take the derivative of the tangent function. That is secant squared x. So this is the full answer for this problem. Okay, so hopefully that made sense to everybody. Not seeing any questions. So, okay, then D is product rule. Okay, so product rule, first I'll take the derivative of the square root function. We then just tack on this the secant, and then we say plus square root of t times derivative of secant. Derivative of secant is just secant tangent. And I'm being careful to use the t's because this function is written in terms of t. So you should always try to use the same variable that you're given. Okay, E. Well, isn't it great that I told you that generalized product rule? So this is exactly where you would want to use that instead of using product rule twice. So, so if you don't remember, it's each term. This is going to have 3 terms. Each term, that one of them is going to be derived, and the other 2 are just copied directly. So the first one I'll do is I'll take the derivative of sine, which will be cosine. And then since we actually will have 2 cosines, we may as well just bring those together. Then the second term, I would take the derivative of cosine, which will be negative sine. Okay, so actually this should be a minus, not a plus. And then the sine will combine with the other signs. We have sine squared times tangent. And then the last term is we're going to take the derivative of tangent, which will give me secant squared. So then we have a plus sine x cosine. I need to write a little cosine x and then secant squared x. And actually, well, there is one thing you could do. Secant squared. I mean, secant squared is actually cosine squared in the denominator, so you could actually simplify that a little. But let's not bother with that. We'll just we could simplify this one also. Oh well, yeah, just leave it like that because in this format at least, it's very clear how you got to this answer. Don't want to do extra work and then like accidentally mess things up. All right, F. Well, oh, it's actually 4 chain rules or 3 chain rules, 4 functions, because this 7 theta is also a function. So you can get something that comes out when you take its derivative. All right. Well, so you'll see like this is really just unnesting things. So first we take the derivative of sine, which will be cosine. Then we just copy down the contents. So you got sine of cosine of 7 theta, and then just close up the parentheses, 1, 2, 3, I think. Okay, and then times. So next I'm looking at the inner function, which is the sine of cosine of 7 theta, and I'm taking its derivative. The sine function is still the outermost thing, so we take that derivative and we'll get a cosine. Okay, now the inner contents are going to be the cosine of 7 theta. So we just copy down cosine of 7 theta, and we have 2 parentheses. And now we look at its inner function, which is cosine 7 theta, and that is what we need to take the derivative of. Cosine is the outermost function, so I'm taking derivative of cosine, which is negative sine, so we have negative sine. And then we just copy down inner function, which is 7 theta. And then I'm taking the derivative of the inner function, which is 7 theta. Derivative of 7 theta is just 7. Okay, so maybe these arrows can help. I'm not sure if they do help or not, but it is kind of like this. I'm taking the derivative of this. Like this is really how I'm viewing it. Is I know I need to take the derivative of the inner function, which is the like chain rule piece that is sort of what keeps on propagating. Okay, and so that's what like creates the following terms afterward, or not terms, but like the factors, the multiplicative factors afterwards. Okay, and then we stop at 7 because there's no more inner functions, right? There's no inner function to 7. All right, so that is number 6. All right, any questions? Hopefully the chain rule made sense. I guess we can keep going. Okay, right, so this is just chain rule, and then you want to evaluate it at 1, right? So when you read this, like what this is asking is find C prime and then plug in 1. So I don't know. Did it make sense previously when I like did everything in one go, or do you actually want to? I guess I'll just write it. Does it make sense how I go from this and I just immediately say it's f prime of g of 1 times g prime of 1? Does that make sense?
Could you say it again?
Say. Well, I'm asking like, does it make sense how I go like how I can immediately conclude? Just I'm taking the derivative and then I'm plugging in at 1. So I'm doing 2 steps, but I'm doing them in one go. So I'm like I can't write both steps out, but okay. So I'm gonna. Your silence makes me think that like this makes sense. But if you don't see it, take the derivative first. First, what you would do is you would do c prime of x, right? And then you would just say plug x equals 1. Plug that in, and you'll get this formula. And so from that, we just have to read off the table correctly. So there's sort of more than one step to this. I have to plug in g of 1. So g of 1 is going to be 4. So that's going to leave me with f prime of 4 here. G prime of 1, I get this value 2. And so now we have f prime of 4, which is 10. So 10 times 2, so we get 20. Okay. Number 8 is just asking us to verify this identity. Okay. Well, so hopefully you had thought about this before coming here and you at least gave it a try. So the approach to doing this is pretty much the same thing as how he shows the rule for tangent. You're just doing pretty much exactly the same thing. So what you do is you first rewrite cotangent as being the ratio that it is. So cotangent of theta, this is just dd theta of cotangent is just cosine. Oh, I should not put an equals there in that case. Is just cosine over sine, which is exactly why you can think of this as a quotient rule. So you just apply quotient rule, which gets rid of this derivative operation because we're now taking the derivative. Quotient rule says sine theta times times the, wait, what am I doing? Yeah, times the derivative of cosine, which is going to be negative. So we get a sine squared, and then we would have a minus, and then cosine times derivative of sine. So that's going to be cosine squared theta, and then all over sine squared. Okay. And then you have to know the Pythagorean identity. So there's in trigonometry, there's something called a Pythagorean identity, which says that sine squared plus cosine squared is equal to 1. So you see that you have sine squared plus cosine. You actually have the negative of it. So imagine that you pull out a negative, then what you end up getting is a -1 on top. And then you have sine squared in the bottom, which is just cosecant squared. Okay. And so that's how the whole proof goes. It's as long as you're comfortable with your trigonometry, this is pretty much, I think it's pretty straightforward. Any questions on this? Did any of these equalities not make sense? No, everyone thinks it makes sense. Okay. This was a shorter problem set than I thought. I guess maybe I'll have to just do both for the other class too. Okay, well, this function actually I had to do a couple times because it's a bit more involved. So the units for this problem, that's kind of the first thing that you need to notice and to keep track of. So thankfully, there's no conversions that are necessary. So the population is in thousands. This is measuring, parts per million, but thankfully P of T is also measuring thousands of people. So you can just feed it right into the carbon monoxide function here. The question is asking the rate of carbon monoxide, the rate that the carbon monoxide be changing 5 years from now. So this is really where the question is. And so the way we would interpret this mathematically is it's asking for the time derivative of P of T. And then we want to evaluate this at T equals 5. So this evaluation bar just means after we've gotten this function in terms of time, we're going to plug in at time equals 5 years. So yeah, what's tricky is how do you actually take the derivative of this function, I guess. Well, how do I want to explain this? So definitely you see that there's a chain rule here, and you see that we're going to plug in 5. So similar to number 7, where we could just write it out in the form where it's already plugged in, we can also do the same thing here. So we want to take a derivative of the carbon monoxide function, and then we're going to have to plug in P at 5, and then we're going to multiply at P prime at 5. Okay, so we need these two numbers in order to get our answer. And we can calculate these two numbers separately. The real reason why I want to do this is because I don't want to create that combined function. I don't want to create the carbon monoxide function composed with the population because it's already got a square root. This is already going to be something squared. It's going to look really terrible. So I don't want to create that combined function, then take its derivative. So instead, I want to break it up a little bit as much as I can. Okay, so this says I need to do a few things, right? I'm going to need P of 5 at the very least. Well, P of 5 is pretty easy to compute, actually. We can just plug into that, and I think I used a calculator for that. Yeah, I think you don't need to, but I did. Okay. And then, well, you also need to feed this value. So it gets fed into the carbon monoxide derivative function. So we need a derivative. And this prime is actually, this derivative is with respect to the variable that it's defined for. So this is actually the derivative with respect to P. So this is why I have to calculate dp of CO of P, which is, as you know, you take the derivative of the square root function. You have like so. But then you have a chain rule because the inner function is not just something simple. So you have to take the derivative. That's going to be a 0.5 or a 1/2. Okay, so, and you could rewrite that, but I guess we don't really need to. Yeah. So then the next thing is so now we have, what do I want to do? I want to say that this is the CO prime function. Okay. So then the next thing that you would calculate is you calculate CO prime evaluated at 101, because that's what this requires you to do. And when you plug that in, definitely you want to use a calculator for that. You get this value. So we get 0.031. I could show you all these calculations, but we're already close to being over time, or we might even be over time now. P prime is straightforward, I would say. So P prime of 5, first I need P prime of T. So I take the derivative of the P function, that's going to be 0.08 T. And then I just plug in 5 to that. Did I put that? Yeah, it's 0.4. So I have this decimal times this decimal, and that is going to yield me the value 0.0124. And we should put units since this whole problem is like a word problem, there are units. This is parts per million of of carbon monoxide per year. So this is the rate that you expect the carbon monoxide level to be changing. I tried actually to figure out if this quantity makes sense in real life. I think that these numbers aren't really realistic. I don't know. Did anyone else do this problem and they got like a different answer? I guess that's what we should confirm. Okay, well, did this process make sense to you? Or is there some other questions you want to ask me about this? Or the rest of the sheet, since we're sort of a bit over time now. No one has questions. Okay, then I'm gonna stop the recording.